Okay, hello everybody. Thanks for joining today to this tutorial about machine learning with software performance. My name is Puyan Jamshidi. I'm assistant professor at the University of South Carolina, and I'm delighted and honored to be with you today discussing some exciting topic on optimization, on transfer learning, and more recently about some counterfactual causal reasoning related to performance. So basically, today we have some short breaks in the middle of the talk, about 3-4 minutes. We may consider 2 of these short breaks, depends on the audience. And I would like this tutorial to be very much interactive. So please feel free to ask your question. You can ask it through the app that you have, the ASE organizer provided. Also, you can unmute yourself and enable your webcam and talk and ask your interesting questions. So I would like this tutorial to be very much interactive. So please help with this. Before we jump into detail, I have to mention that we have a lab. We look into some topics at the intersection of machine learning systems and autonomous systems specifically. And we are interested into mainly transfer learning. Related to transfer learning, we look into causal invariances because this is also important for learning important features in the data. We also look into structural learning, concept learning, and physics-informed learning. And our research is proudly funded by NSF and NASA, and we thank them for supporting our research. I have to mention that the topic that I will present today, actually, I have been only a very, very small part of it. So I'm just here to present what this fantastic team has already done. So I'm just a presenter today. Whatever I discuss mainly has been done by our fantastic collaborator. Recently, we started collaborating with Rahul and Bashaki Ray from Columbia University. Shahriar from my team is leading the effort with respect to the performance optimization, and some part of this work that I'm presenting today, especially about causal inference, is led by Rahul and Shahriar. Also, Muhammad Ali Javidian was a postdoc in my group. Now he joined to Purdue. We also collaborate with Christian Kastner and Miguel. Miguel looking into very related topic on white box performance analysis. And for all of these performance related topic, we also collaborate with Norbert from Leipzig, Sven, Lars, Marco Valtorta, he's a colleague of mine in causality, Vivek now at Facebook, and Tim Mencius at NCSU. So basically to emphasize, I'm just a presenter today. The main work has been done by this fantastic team. To start by giving you some motivation, what we are talking today, we know that we have many different applications nowadays in our mobile devices or watches or whatever we have around us. Typically, they run different tasks, and these tasks are covered by some sort of machine learning systems, more or less deep neural networks. Obviously, it would be fantastic to get accurate prediction of what the camera sees surrounding us. We don't want to be inaccurate. We don't want to get fat as a result of bad prediction, what is the amount of calorie in the food. But on the other hand, we wouldn't be so happy if we ran out of battery quite soon just because we are using these fantastic machine learning systems. So the goal is to reason about performance. And we know that performance is a multi-objective thing. And it's not really easy without any tool or support to reason about performance and make trade-offs. So this trade-off with respect to performance is the key indicator or key objective that connects everything that I will talk today. We know that these days many systems are built configurable from big data systems such as Apache Hadoop to robotics. And more recently, as I mentioned, these machine learning systems means that they expose a bunch of different configuration options where end user can configure. Let's look at one particular example, in this case, Apache Hadoop. We know that big data engine, such as Apache Hadoop, expose different configurable options. For example, here we have the number of threads that the end user can change. Here is 64. Obviously, user can play around, change it to 32 or more number of threads, and it could set any number of any integer for these particular options. We also have here the amount of memory that the JVM machine wants to consume. Obviously, the end user can change this to any integer number technically to improve the performance and get a better trade-off if they have multiple objectives. But we know that at the end of the day, this is not really easy. There are some constraints. I'm sure you have faced and tried to change these values, and sometimes the system crashes, and sometimes you run into some unexpected performance issue. For example, if you increase the number of threads, sometimes you observe that not only you improve latency, for example, but also your latency has been deteriorated as a result. And these many options in this slide is only a small part of the whole configuration space that we are talking about. So we have numerous options for real-world systems these days that is not easy to reason about. People have looked at these increase in terms of configurable options over time. And for example, in this case, Tianying looked at Apache Hadoop from 2006 to 2014, and he observed that the number of options has increased quite considerably. In this case, it started from somewhere 18 number of options from 2006, and 2014, it ended up something around 180. So you see that the number of options has increased from 18 to 180 only less than 10 years. So this means that the configuration space, if we reason about the size of the configuration space, actually is reason from 280 to 2 over 18, even if we assume that these are binary options. So you see that the scale that we are talking about is this amount of increase in terms of the change in the size of the configuration space, which is massive. This is massive to reason about performance and find a reasonable configuration. If it was reasonable here, it is not reasonable at the moment. And this trend was similar across other type of systems. So it was not only related to big data engine, but also for a storage application, for MySQL, for example, for web servers. And so many other type of applications, this increase in terms of configuration space was and has been and is still coming. So let's look at some specific why configuration matters. We know that by looking at the code, the key reason how changing configuration of the system deteriorate or improve performance is that the code path that gets executed on piece of hardware would be determined by the exact values of these options. For example, these particular options for very simple piece of code would determine either one line of code get executed or multiple lines of code get executed as a result of a specific value for this one option, right? And the developers or end user of the system are interested to know if I change this, whether I get a boost in terms of a speed or my energy consumption would be deteriorated as a result. So reasoning in this multi-objective space is really the key objective of developers, and these are some specific questions they want to answer. For example, they would like to understand performance behavior of such system, especially at a scale into massive configuration space, and they want to be able to reason about these configuration changes, as I mentioned, and make some trade-off, right? And when we say trade-off, maybe in some situation, it would make more sense to increase latency because we want to consume less amount of energy, right? So we might be able to sacrifice one objective in order to gain performance in other dimensions in the objective space. So this trade-off actually matters a lot. And to clarify, when we talk about configuration of the system here, we say system, and system is not only code. We talk about configuration space across a stack, and this is also important because people have looked at the configuration, optimization of configuration, and also understanding the configuration space only at the software level, where we have some code, but actually there is much more than that down the line, specifically the modern hardware architectures are highly configurable. The embedded systems, these kind of IoT devices, all configurable at the macro architecture level. They expose many interesting configuration options, and these options would interact with the options that developers have at the software level. Even if we assume that we test the system, the software itself with several hardware, several environments, there always would be new piece of hardware that comes into the place, and when we deploy the system into this new macro architecture, there would be new and unexpected interactions that may happen as a result. So when I talk about configuration space, we talk about cross stack. Some of the options are related to the hardware, some of the options are related to kernel and middleware, and some of the options are related to the software. To clarify, for example, we might have different types of systems. And more interesting type of systems are the composed system, where we have multiple different nodes, either could be deployed in even single node. Imagine that we have some camera that capture what's going on in the world, installed on top of a parking place, right? And we have some backend image classifier and segmentation. So in the pipeline, we segmentize the video and then would feed different part of the segmentation to some classifier to identify what is in the image. So we have a composite system that might sit in an embedded hardware like NVIDIA Xavier or so on, and do some down the line analysis. This could be even more interesting when we have multiple nodes that within this composed pipeline, we might deploy part of the pipeline on one piece of hardware and part of the pipeline on another piece of hardware. And this, in terms of microarchitecture, there might be totally different with respect to the type of resources they provide for machine learning tasks. Or you may think about some IoT kind of systems where part of the systems is deployed on a specific device. Part of the system is actually deployed on cloud. So for example, you might have some down the line analysis in Amazon doing some data streaming when this data is collected by these Raspberry Pi devices and do some, for example, some interesting streaming jobs at the backend in the cloud. And typically in these scenarios, we do not have access and we do not know actually what kind of microarchitecture is used for deploying these tasks at all. So this is not under our control, and without having any tool to explore these interactions would be impossible to, and it would be very likely to run into some performance faults. Or you could think of some distributed big data applications where it composed of multiple different tasks, like MapReduce, where even each of your map could be one neural network running on another piece of hardware. So you have a totally distributed setting where part of you have heterogeneous tasks as a part of the whole architecture that composed in a with different tools, with different structure and architecture, and deployed on heterogeneous microarchitectures. So you might also consider some cyber physical system like self-driving cars, where actually part of the hardware is even not directly accessible for your debugging purposes, and you need to remotely debug the system. So you have these kind of constraints as well. Or even in event-driven system, you might have multiple clouds, not only one. You have heterogeneous hardware, but also now these heterogeneous hardware are managed by different cloud platforms that they come with different characteristics and limitations. So you have a variety of different deployment environments that are heterogeneous with respect to both software level as well as the hardware level, and the way and the constraint that you have for each. So these provide some different category of system that really makes a difference how to reason about performance and what you can do and you cannot do with this trade-off space. So hopefully this provided enough motivation of what I'm going to talk about. So today I start with some specific case study. Then I talk about some transfer learning scenarios, some empirical understanding of performance space, and as well as some guided sampling. And at the end, I will mention about the current research that we are doing. Depending on the time and how much time will be left, because again, I would like to emphasize that this would be very much interactive. This is the way how I would like it to be. To at least, I would like to learn from you, get your interesting questions. Um, so, and I would probably would like to spend more time on the current research we are doing, specifically in terms of performance optimization, as well as this recent work that we started doing in terms of um, exploiting causal inference for reasoning about performance and finding performance faults. So I may skip some of these uh, middle steps depending on the time. Is there any question here? Okay, let's continue. So specifically, the case study was a system that I have been dealing several years ago, and that was a composed system with interesting functionality. It has several different functionality, but the main purpose of this system was to identify trending topics in social media. And the user were able to actually define different topics, and they were also able to search within the content. They were able to subscribe to a specific content and so on. Let's look at the architecture of this composed system. So it has a crawler. This crawler searches through social media and collect, for example, tweets with certain speed, and then store this content into a storage such as Apache Cassandra. And then this system had an orchestrator mainly based on Apache Storm, another big data engine, which then fetch the content every 10 minutes with certain number of tweets, 100K number of tweets each 10 minutes, and push this content in the down the line content analysis that was powered by Apache Solr. And then the whole system enable search for these contents for end user, and also the integration for third-party applications. So it was as you see, is a kind of linear pipeline, and this type of architecture is quite common for big data systems, and basically and that's why I chosen to specifically discuss about this, because it provides some interesting scenario that makes it interesting. So let's look at the challenges. So the stakeholder of the system at the time wanted to increase the number of users to 200 more. So they wanted to invest and also increase the number of users. This is what their objective was. Based on some performance analysis, we came up that in order to scale to this number of users, this number of bursts in the request and everything, we needed to speed up some part of this pipeline. Specifically, we needed to speed up this crawling speed 10 times faster. And also we needed to make this fetching time closer to real time. It was 100K tweets per 10 minutes, which was considerably slow for this surge in the number of users. So this was based on some performance analysis, based on some modeling of the system, understanding of the system. And the question was that, maybe it's not too difficult. Maybe we could increase the resources. We could buy more servers, and we can increase the resources to maybe 100 times more, and that would be fine. Yes, but obviously this comes with a cost. We thought maybe this is a good scenario for exploring configuration space, see whether we can get any better performance with the configuration of the system, specifically at the composed level. Let's look at the opportunities, what we have got here. We had Apache Cassandra in the pipeline. We also had Storm, and we had Apache Solar. These were three engines in the pipeline that we discussed. We know that all of these are configurable. Even if we imagine that we have 100 options for each of these systems, and if these options are only binary, the way how we structure the system in a pipeline, it was a kind of linear structure. We know that any change would be interacting with the other components, right? So as a result, based on this typical architecture, we would have this amount of possible configuration for the system, even for this simplistic assumption that these options are just binary. So we know that this is a massive configuration space, and these number of options, these number of configurations are more than the estimated number of atoms in the universe. And within these massive scale, it would be difficult to reason what is the best configuration. Is this the best configuration or this one? So we are dealing with the massive configuration space, and due to the characteristic of this space that I'm going to talk about, it would be difficult to reason about this without any proper tooling. So specifically about Apache Cassandra, we look at this configuration. This is the performance of the configuration. So let me clarify, each dot represents one configuration for this component, right? And we measured write latency for this, as well as the throughput for this particular component in the pipeline. So each configuration, you can find its corresponding throughput and write latency. This was the default configuration for Apache Cassandra. So as you can see, is really bad. It's located in the upper percentile with respect to the write latency, and is actually located into the lower percentile with respect to the throughput. So it's not really a good configuration to start with. So this was this red dot was corresponding to the configuration that was recommended by the expert. They had domain expert for this system. He had massive experience with respect to the internals of the system and so on. But this was the configuration that was recommended by this expert, this domain expert. You see that it's much better with respect to the write latency, but nowhere near the optimal configuration, specifically with respect to the throughput. And we know that this is the optimal configuration. We want to get here. We want to decrease the write latency and increase the throughput for the system. And you see, more interestingly, you have so many different configurations that are similar with respect to the write latency, but massively different between the throughput of the system. So this would make it really difficult to get here from somewhere here, right? So it was very challenging configuration space to reason about any performance, specifically when we have multiple objectives. It was similar, very similar for a Storm as well. So I'm not going to repeat these, but basically default configuration was bad. Even worse, the recommended configuration by the expert, and this has been the optimal configuration, as you can see. So overall, if I want to summarize, the default configuration is typically bad. Optimal configuration is could be even 10 times faster than the worst configuration of the system. And this is noticeably faster than even the median performance of the system. So these were some observations from empirical results, and I have to mention that these configurations were sampled randomly. We just wanted to understand what are the opportunities there. We did not intend to do any optimization, just wanted to understand the space. At the end, I don't want to go into the detail, but we were able to actually develop an optimizer, performance optimization approach based on some Bayesian optimization technique that we developed that was able to scale up the system to be able to find reasonable and optimal configuration for the system that without increasing any resources and even decreasing 20% of the resources was able to serve this scale and always we outperformed the recommendation by the expert, the kind of configuration that was suggested by this optimization approach. Okay, so far what we have discussed was basically giving you some particular example, particular case study, why, what are the opportunities for any design space exploration or optimization for highly configurable systems, right? But beyond these opportunities, beyond the capabilities that highly configurable systems provide, and at the end of the day, these highly configurable systems are fantastic for many stakeholders. We know the reason, right? The configuration would enable stakeholders to customize a product for a specific user, right? So there wouldn't be any need for doing code changes. One can configure the system and fit it for a specific end user. And this is the way how product line or configurable system works. And there are some other reasons beyond this, but these are fantastic, right? But it comes with some cost. And the key thing is that even we are able to optimize performance, but due to these massive interactions, there would be some unknown performance faults that cause the system to either perform badly or not gaining any performance boost, even if we change the resources, underlying resources, right? So let me clarify this by specific examples. I'm going to talk about two very specific examples from by looking at some machine learning systems which were deployed on NVIDIA hardware, right? So this one was a bug report when the end user were changing the hardware from TX1 to TX2. TX1 and TX2 are some NVIDIA hardware with different macro architecture. And when the user changed the hardware, we know that TX2 has much more capability in terms of the hardware resources. So they expected to see 30 to 40% boost with respect to the performance. In this case was the latency of the inference of this machine learning system. But at the end, not only they did not observe this boost, but also they observed that the performance of the system was twice slower, and that was weird, right? Isn't it? After looking into some detail, they found out that they need to change the configuration of the system, right? Specifically in the target hardware, there were some misconfiguration. Some of the CUDA options, some of the GPU, CPU modes option, and some fan mode options were set incorrectly. And as a result of this, and because these interact and these interactions were unknown even to the developer of the system, it took really a long time. It took over a month for them to find out the reason, the root causes for the performance of the system. Also, more interestingly, there was another issue. It was the case when they used some image classification. They migrated from this image classification from some Raspberry Pi hardware to TX2. And again, they expected to see some performance boost, and this is totally about the expectation, right? If you look at this conversation, the user, this guy, was expected to see really a better performance, and it was surprised why it took the same time for doing this inference. Even migrating from some small hardware to TX2, which has much more resources. You can even run a self-driving car on TX2. So it has this much resources, nowhere near Raspberry Pi resources. And also, the more important thing is that in terms of microarchitecture, there are differences, much differences between the architecture, like ARM architecture, like Raspberry Pi, or something like TX2. And again, interestingly, they found out that the reason is related to configuration. Specifically, here was CPU GPU frequency that needed to set. So that was the suggestion by NVIDIA, right? The developers of this hardware to get a better boost, but also surprisingly, after this guy tried this suggestion, it didn't work, right? It didn't work, and then NVIDIA suggested another option, swap memory in this case. So this remind us that it is not really easy even for the developer of the system to reason about performance in this highly configurable space, right? So even the developer of such system would not be able to make this trade-off, find reasonable repair to fix these issues, because of the same reason that I mentioned. And these things could happen as a result of these unexpected interactions between options. And more importantly, end user want to understand this. They want to find out if they change, for example, something like swap memory, what would be the effect? What would be the effect of this change in terms of performance, right? So there are concern about the implication of these changes to the configuration. And you see that, like, again, for these cases, it took a long time until they found some solution, some changes to the configuration that could fix the bug, the performance bug. I'm going to talk about later on about our current effort in terms of providing end user some mechanism that they could reason about these root causes to fix some of these performance issues much faster with less cost. And that's why I brought it up in this context. And if, again, I would like to emphasize that we are talking about a multi-objective space, right? And within this multi-objective space, we have this performance. If we look at performance distribution of the system, we know that empirically performance distribution are multi-modals, right? So for different objectives, right? Here we are talking about latency, right? We are talking about the energy consumptions. We have many configurations that are located in an okay zone, meaning that they're performing, they're located in the first mode of this performance, which is okay with respect to latency, also okay with respect to the energy consumption. But we have three other zones. One is we have so many and considerable number of configurations that are even that are either worse and performing badly with respect to one, right? For example, these bunch of configurations are doing very badly with respect to latency, right? But doing fine with respect to energy consumption. These configurations are doing okay with respect to latency, but on the other hand, they're located in a part of the space that performing poorly with respect to energy consumption. And we have considerable number of configurations that are doing very badly with respect to both objectives. And we have to distinguish this, these three zones, because it is relevant. Again, it is relevant about this trade-off. We want to make trade-off. Maybe if we have an issue with respect to latency, maybe we optimize it with respect to latency. Maybe we find a good configuration that decreases the latency to a very small one. But on the other hand, we make the other objective energy consumption worse. And this can happen a lot when we optimize with respect to one objective rather than the other. This motivates the effort in multi-objective optimization approaches. So far, what we have discussed was mainly elaborating on what is the configuration space, right? What we are talking about, the trade-off, what type of system might be relevant for this trade-off, right? We looked at some real performance issues, right? Also, we looked at, before these real performance issues, we looked at the opportunities, right? In terms of performance optimization, with respect to this particular case study that I mentioned about. So all of these provide some foundation for the work that I'm going to present, because some of which are related to optimizing performance or exploring the space, some of which are actually related to how we can reason and debug performance, how we can fix or repair performance, right? So we are talking about multiple different directions. Hopefully this provides some foundation to see the differences and see why I provided this foundation. Is there any question here? Oh, there is a question from Fatima. Thanks for asking. How do you calculate the energy consumption in your studies? Oh, by the way, here we have Rahul and Shahriar. So Rahul and Shahriar, wherever you think you can jump in and provide better explanation. This is the work you guys have done, right? Please jump in and answer these questions. I'm sure you have better insight than me. So to elaborate on energy consumption, the way how we do it, we basically, here is how we work. We change configuration, we fix the configuration, we deploy the system on piece of hardware, and we instrument the system. So for example, in TX1 board, maybe Shahriar can show you, we have different sensors on the board. And we can read from these sensors from different part of the board with different granularity at any time, in real time really. So when we are running this task, how much energy it was consumed by CPU, by GPU, by memory, and the total as a board. So we have different sensors to measure all of this, both at the granular level, like CPU, GPU, memory, and also at the aggregate level for the board level, right? So there are different granularity with respect to these performance measurements, mainly all of which are done actually through instrumentation, right? So this is about energy consumption, and most of these energy consumption measurements, as well as the heat, right? I have to mention that we are able to measure the heat of the system, the heat that the system produces when running tasks on these boards, because we have like quite good number of sensors on the board to measure all of these. Some of these measurements, I have to mention that really you need to instrument the code. So for example, the work that Miguel is doing for white box analysis, he's doing mainly is instrumenting part of the code, and when running these analysis, he measure, okay, how long does it take from this to this, and measure the difference, and that is the performance under this particular configuration. So I hope this answered your question, Fatima.
Yeah, thank you. So I first of all, thanks for all of your tutorial. I was pretty like waiting for Friday. So this is Friday morning. I was pretty waiting the whole week to see this tutorial. And I find it very, very useful actually. Thank you for your talk. So just as a side note, is the energy consumption something that industry is also like looking for to decrease it, or it is part of I know we are not discussing about the environmental, climate change, etc., and the global warming, but other than like having those big data centers, for example, to save some energy, at what level the industry is interested in decreasing the energy consumption?
Yeah, that's fantastic question. Thanks, Fatima, for joining us. Thanks a lot. I really appreciate it. That's a fantastic question, right? So energy consumption really, and these different metric really depends on the application, right? Definitely in some scenarios, some of these energy consumption matters a lot, specifically when we are running these tasks on piece of hardware where we have limited resources, right? So for example, when you deploy TX2 for running tasks for localization of the robot, then uh, energy consumption matters a lot, specifically for machine learning tasks. They have some nuance kind of details that, for example, we know that in deep neural network, reading from memory is a kind of operation that consume different order of magnitude energy than doing numerical calculations. So you don't want to have access to the memory a lot, and you could have the same latency for your inference, but considerably different energy consumption for the same task, right? Depends on your architecture, depends on the way how you consider um, accessing the memory and what type of memory, right? This makes a massive difference in terms of energy consumption, and this matters a lot. For example, for robotics tasks, for when you deploy these systems on your watch, right? You have limited resources there, or other type of resource constraints environment. So this matters a lot for this scenario. Heat also sometimes matters, right? So when you deploy these systems on some robots that goes underwater, right? So it may travel some part of the water that is hot. And if you're doing the same sort of task, then you may blow up the whole thing if you don't reason about heat dissipation, right? So it really depends on the type of applications that we are talking about. Um, and and definitely would, and we noticed about these different performance like energy consumption. Maybe Rahul can help here, whether he has any particular example of these scenarios when he looked at these issues, performance issues. But these,
Sure.
yeah.
Yeah, I think they're also, I would just add that they're also related. So for example, with heat, you wouldn't want the system to thermal throttle, right? So if you have a configuration that leads to a high heat dissipation, the internal mechanisms will automatically bring down the latency and the CPU frequency so that as a thermal throttling failsafe. So that it's really important to look at them even from a latencies perspective.
Thanks, Rahul. That's fantastic. Miguel is asking how noisy or consistent is measuring energy consumption. That's also a fantastic question. Thanks, Miguel, for asking. As far as I know, Shahriar could elaborate on this. The measurements of heat is very noisy. So we were not really able to measure heat in with the accuracy that we wanted to have. Measuring energy was also noisier than latency. Latency was probably the most accurate measurement we could do because we are measuring time and it's accurate, right? We know how to instrument the code and everything to get it with the certain accuracy level we wanted to. But the other objectives are much more noisy. Shahriar, do you have anything to add here?
Nothing much, yeah. But for energy consumption, the distant devices that we are using currently that uses INA to 6 monitor, I think that is the sensors currently state of the art for measuring energy, and which they claim to be very accurate. And I think the noise level is not that higher. So, and also even for tackling those, we measure those configurations repeated times, mostly 5 to 10 times to then take the median. Or so that's what we do to encounter the noise. But for energy also, we found that it's not that noisy as it is with respect to heat. So I cannot actually quantify how, but that's what I should say. Like we can compare with different partners of the field.
Fantastic. Thanks, Javier. Yeah, bottom is also mentioned in the about TinyML. Yes, exactly. That's a good scenario. In those cases where TinyML is used, especially for mobile devices, this is um, where energy consumption comes into the place. Thanks. Fantastic discussion. Maybe let's have 3 minutes break, and then we start after 3 minutes. Make sure you come back after 3 minutes. Let's uh, let's have this break, and let's start shortly. Okay. So let's start again. So now let's talk about some more detail about the setting, because this would help us to understand the detail. So far, for those who are not familiar with this line of research, with this line of work, maybe it was somehow too abstract. So this hopefully would help you guys to um, to to become more concrete and understand in a better way. Um, so let's imagine that we have a particular configurable systems here. Let's imagine we have a compiler, and then we have a bunch of different options. And these options, these are the configurable options that we talk about, right? Mathematically, we represent it as the joint product of these all options, right? And this could be, for example, for the compiler, could be about disabling or enabling dead code removal, right? Could be about constant folding, loop unrolling, or function inlining. These are particular optimization that are exposed in the compiler in order to optimize the code that is compiled by this compiler, right? So these are different options that you can change for this particular compiler, right? And we call this the configuration space. So this is mathematically the configuration space that we talk about, right? And then we have a program which for which we configure the compiler. In this case, we enable function inlining, right? And we disable all other optimization available for this compiler. And then we compile the program, this program with a specific configuration of this compiler, this particular with C1. We compile the code and we deploy it on piece of hardware, right? We have a specific hardware environment, and this is what we call environment, right? We have some binary that sits on hardware, and we are able to instrument it and measure performance. This is the kind of setting typically we have. And then we have multiple objectives, right? We can think about it as different functions. We have compile time specifically for this configurable system, and compile time and all of these objectives really depends on particular configuration that we have for the system. In this case, compile time was 11.1 millisecond, right? We have execution time, we have energy consumption, and we can measure it the way how we instrument the system, right? So we have some measurements for the system, each of which is associated to particular configuration. Obviously, if we change this configuration, all of these metrics would be different. So if we enable loop unrolling, the compile time would be increasing because we are running two optimizations. So that's about compile time. The execution time may decrease if this loop unrolling would be good optimization for this program, as well as the energy consumption may also change. We don't know, depends on this kind of optimization and the interactions that it has with this particular hardware. So even one optimization may result in decrease in one microarchitecture and increase in other microarchitecture. Really depends on particular environment that this piece of software is deployed on. So this is about the whole setting or mathematical or abstract representation of this configuration, both at the configuration space and the objective space. So this is the objective space we're talking about. And then a typical approach for understanding performance behavior is doing some sensitivity analysis. So we have a bunch of different configuration. Configuration is particular instantiation for each options, right? We collect a bunch of data. Data is basically measurement with respect to particular objectives that we have. And then we use part of the data for training a model. This model, typically in black box approaches, is sort of machine learning model, is a black box model. And then we use this, and this could be like, let's say this black box model could be something like Gaussian processes, could be in terms of a decision tree or random forest, could be in terms of even neural network, right? Could be any black box model, right? Probably for performance behavior, you don't need neural network. And if you are interested, I can tell you why. But typically, typically you can use any sort of black box model to give you a approximation of the underlying performance behavior. So F is the underlying performance behavior, the true performance behavior. F hat is the approximation that you can get based on limited data and the particular expressive power that you get from this black box model. And we know that the hypothesis space that these models could support would be different, right? Some of these are highly nonlinear, some of these are linear essentially, and they could support different hypothesis space at the mathematical level that I'm talking about. Then once we learn this function approximation, we can test it, how good it is, because we have the ground truth for many configuration, and if you are talking about a smaller configuration space, maybe we are able to measure all of these configuration. If you are talking about larger, so for example, for 20 options, we know that these are binary, we have 2 over 20 options. It is not impossible. Obviously, we can measure 2 over 20 configuration if we have like several months, and this is what we did, right, for some of the experiment, but it takes several months. It does not take several years, several months. You can do it. But for some larger configuration space, it may take even beyond 100 years. So, and then once you have some ground truth data, you use some metrics to measure the accuracy of your function representation, right? So here, for example, you use particular metric to measure the difference for each configuration from what your model provided as an approximation and what you have observed empirically for the system. And then you can report the error. This is the way how typically black box setting would work. And then when we call performance model, again, mathematically, this is easy to imagine. We can consider a performance model as a mapping between configuration space to some real value. And this mapping could be a function again that has different hypotheses. In this particular, we are using polynomial regression model where your model is some sort of linear with respect to these options. It also shows some interactions as well. So you have a bunch of options. You have the coefficients for each term, and also you have some interactions. This means that, for example, for example, for this particular system, right, we have one option. And imagine that this is the underlying performance behavior. If you enable this option, this is the performance that you would expect to see. And if you disable it, this is the performance you would be able to see. And this is the representation for the performance model. So when we talk about performance model, this could be in terms of something expressive, like this type of model, a polynomial regression model, or it could be in terms of something black box, right? For example, a decision tree, or a Gaussian process where you cannot see inside, but you can plug in your input and you can get the output, right? But all of these representation really is just a matter of mathematical expression of your model. You can call them model. Again, they provide different accuracy. They can support different hypothesis space, and some of them are expressive, some of them are less expressive, some of them are explainable, some of them are not explainable. So you can have a variety of different performance models for the system. Yes. Do you have any question about these settings? And typically, the way how you approach this, you have a system, you configure the system, and then you measure performance. So you have this type of space. I mean, this is like we are talking about one dimension really, but like one dimension is naive. Typically, you have many dimensions, and you measure performance, and you can get some mathematical representation of your performance behavior. And obviously, within this space, you are not able to measure all configuration, but you want to have some extrapolation for the configuration that you have not measured using the expressive power of the model. Obviously, in this setting, you could exploit some simulator that provide you measurements, your performance evaluation, but this comes with some noise. For example, you might have, if you use, so it depends on the fidelity of this simulator. So typically for any system, you might have different simulator, you might have different, even for example, if you imagine a chemical system, right? For chemical system, you have simulator in the sense of PDEs, right? So you can get the physical characteristic of your material by running an analysis based on the PDE model and get the measurement without even creating such material. Very much similar here. Obviously, some analyses are more accurate, but obviously more costly. Some analysis, some simulator have less fidelity to the actual system, but they can give you the data faster. And in the context of transfer learning, when we talk about transfer learning, we are talking about the situation where we want to have some reuse across environments, right? We have some source environments where basically we are given some performance measurements in one environment, and then we would like to extract some knowledge, some model from the data and reuse this in the target environment. And the key reason for this is that there are several reasons. One reason could be like in target environment, measurements are costly, right? We do not want to measure a lot of configuration in the target environment, right? Imagine a scenario where we have a software in Canary deployment, and when we want to move to production, right? We may be able to get a lot of measurements in this Canary deployment because we may be able to change configuration and disrupt the system and test the system, do whatever we want, because this is Canary deployment, right? But production is sometimes even impossible to change or disrupt the system. We don't want to do that. We just want to observe the performance. That's it. We don't want to disturb the system. So some intervention may be even impossible to do in some environment. But again, we would like to have some way to reason about performance in the target environment, using some invariances that you could discover, right? Using some models that you could discover from the source environment. And this is very much related to transfer learning, right? Unfortunately, we don't have much time that that I wanted to discuss about transfer learning. Transfer learning is a topic that I'm super excited about, and most of the work we do is somehow one way or another is related to transfer learning. But I would like to maybe discuss more with respect to the recent work we are doing with causal inference. I would like to spend some more time with that. So I may need to skip some of the slides in the middle. Specifically, probably we don't need to talk about some of the setting here, but again, related to some of the previous work we have done, for example, one type of transfer learning was related to multitask learning, right? So multitask is the situation where we have some simulator. Again, I mentioned that we can get a lot of data from simulator with considerably less cost, but we can also instrument the real system and get some data there. And in multitask setting, we were interested, can we use both to learn something useful for the system and reason about performance and optimize performance. And for the robotic setting, actually we did that, and we collect some data from Gazebo. We did some multitask learning. We then exploited both source and target to learn some performance model for the system, and then we use this performance model for some down the line analysis, specifically for optimizing, for example, the best configuration of the system. In this work, we used some model due to some reason, like we used Gaussian processes because it provided not only the mean estimation, but also some uncertainty about the confidence of the model. So, and we exploited the confidence mainly to explore the configuration space. That was a perfect mean to explore the space in the principled way that we could reason. So wherever we have observation, you see that like the confidence is quite high, meaning that the uncertainty is low because we know. But wherever we don't have measurements, you see that the confidence could be low, meaning that the uncertainty confidence interval could be high, right? And then we could, one exploration strategy could be maybe get the next sample where your uncertainty is highest. This means that you want to increase your confidence about your model iteratively as you move. But there exist many different exploration strategy for exploring the space, and this framework is known as Bayesian optimization. That was the kind of exploration that we did. So basically, we used some selection criteria, and this is the design space that we are dealing, or basically this is the configuration space. We select one configuration, we do the measurements, we update the GP model. Our GP model here is the performance model that we have. And then we updated it, we update the selection criteria, and this would give us, okay, go and measure this configuration. And you can change this selection criteria. It gives you different points in the space, and you can do this iterative approach until you exhaust your budget. You're given, for example, 1 day to find the best configuration that you can come up with. And then once you exhausted your budget, you choose the best configuration that you have selected in this iterative process. That was the overall approach that we did. There are some mathematics. I don't want to go into the detail, but basically the key intuition was the similarities between the the performance slices that we had across different environments. And these similarities enable us to get a better prediction for the performance model when we use multiple sources, right? So the similarity between multiple sources enable to get and perform better performance. Oh, there is a question. Sorry, Simos. Can we, and if yes, how quantify the correctness of transferable knowledge? Right, that's a perfect question, Simos. Maybe in this case, I hope Muhammad Ali was here, but I'm sure Rahul can answer that. Rahul, do you want to take this answer, this question?
Sure, just one second. Can you repeat the question once more?
So the question is that can we, and if yes, how to quantify the correctness of the transferable knowledge? So imagine that we have, we use this causal model as a transferable knowledge. I will elaborate it shortly, but imagine that from data we learn a causal model. How you want to quantify the correctness?
So there are a couple of ways. The best way to do that right now is at least with causal models is to use some kind of domain expertise. And what we do is we continually gather data and see if the causal model converges. So if we have no domain expertise, then we can use some empirical approaches to find out if we've explored the space enough. If adding new samples doesn't change how the causal model looks or doesn't change the orientation of the causal relationships, then that's one way to determine if the causal model has converged. And we found in our experiments, at least, that we didn't need too many samples before the model converges. But yeah, it could also be like an active learning approach where we get some feedback from domain experts.
Yeah, that is perfect. Perfect answer, right? Thanks, Rahul. Yeah, exactly. This is the case, right? At least with respect to causal models, the typical approach for reasoning about the correctness of the causal model is to ask domain expert, and but there are some automated fashion as well that we can talk about it. Let me wrap up this part, and I would like to jump into the causal work soon, because we don't have much time. But this was part of the DARPA BRASS project that we had. I'm so honored working with CMU guys on this. That was the time I was at CMU. So imagine that we have like each of these dots represent performance of these robots in terms of localization error and CPU utilization, which is approximation of the energy, right? And typically in this case, like the difference of each dot is just the change in terms of number of particles and refinements. And here Miguel can also jump in if I say something inaccurate. Miguel was also part of the work. We were collaborating on this. And in this scenario, one may be interested into finding configuration that are Pareto optimal with respect to both these localization error and utilization, because we want to decrease energy for localization. We don't want to run out of battery on this robot. And at the same time, we would like to be accurate enough, right? So you see here, like we have, even the interesting part is that we have a bunch of different configurations that are providing the same localization error, but while massively different with respect to energy. Even it becomes worse here, right? And that's why multi-objective reasoning or trade-off matters. And typically in this case, we have some constraints with respect to these both objective, and this part provide some sweet spot that we would like to explore. specifically for this transfer learning scenario, we compared against non-transfer learning solution where we only use some prediction, few predictions, in this case 4 prediction in the target environment. Our task was to, so this was the ground truth data, so this was given, and this was target environment that took us 6 months to measure, right? So we wanted to, given this source environment, whether we can predict this target environment quite well. And then we used 4 samples from this target environment and used some sort of modeling to see whether we can predict this landscape well or not, right? And to clarify, the x-axis is the number of particles, y-axis is the number of refinement, and z-axis is basically CPU percentage, approximation of energy, right? And the source is the environment, less noisy, and target is more noisy environment. So we are talking about 2 different environments in this case. Without transfer learning, obviously it didn't work. The prediction that you see is sort of flat, is only accurate across around this configuration that we measured. But using transfer learning, we observed that even with 4 from the target, but exploiting 18 measurement from the source. So using both source and target and feeding both into a multitask learning, we were able to get much better prediction. You see that the model captured the nuances of the change in terms of CPU utilization quite well, although it doesn't understand that this part is not valid, and these white spaces are related to configuration that are invalid. But easily this could be fixed by augmenting this with another classifier that distinguishes between valid and invalid configurations. So that was a kind of experiment, and if you are interested in this, this was a collaboration with Miguel, Norbert, and Prasad and Christian. You can look into more detail. Let's skip this theory building, but basically this theory building was related to some analysis we have done empirically to understand the landscape for different real world systems. And the key observation was that there were some similarities across the environment, that exploiting these similarities would be useful for decreasing the cost of exploration to a good amount. So basically we don't need to explore the whole configuration space, exploiting the knowledge that we could gain, in this case reducing the space dimensionality of the space for this type of highly configurable system. But that was the key takeaway from this empirical study, but we don't have time to go into the detail. And based on this, you can find more info here in this paper. We have done also an empirical understanding from the causal perspective. You know this guy, right? And this is Muhammad Ali. And based on this theoretical understanding, we did some sampling as well. I would skip this sampling part. That was basically a sampling approach that helped us to explore the space, to find interesting sample to learn performance model. So that was a kind of sampling method. For this also Norbert and Miguel were involved. But let's focus on these few minutes that we have. Let's focus on some of the current work that we have been doing. And that's what I would like to spend more time. So one thing that we are doing is about multi-objective optimization. Is mainly the work of Shahriar, enabling exploring the configuration space in the specifically for deep neural network for optimizing performance with respect to latency and energy consumption on some embedded hardware. And this is important for this type of system, again, to emphasize. For example, for this type of system, we observed that for deep neural network, in this particular data set, we observed that we have like massive number of configuration that give us the same accuracy, but massively different, to 22 times different with respect to energy consumption. And that was interesting observation, because really we want to, even though we want to be accurate, but we want to find some configuration here that doesn't consume much, right? We do not like to use this configuration, even though it's accurate, but bad with respect to the energy consumption. You can find more detail here in this paper. This is work mainly done by Shahriar in my lab. But the work that I want to elaborate now is about these causal debugging. This is the work mainly is led by Rahul and Shahriar. And they can jump in and elaborate much more because this is their work. But this is a direction that I'm really excited about. This is something that we will invest for quite a while. This is about exploiting causal inference for reasoning about performance and optimizing performance, right? To motivate the work, in this case, imagine looking only at the data. Imagine that we have this data, we look at, ignore this for now, we look at data, we see that GPU growth as one configuration options is correlated with latency in a nice way. And swap memory is also correlated with latency. But you look at the data, what kind of predictor they are. GPU growth is much better predictor than swap memory because it has less variance for predicting latency, and it's less bias with respect to this performance metric. So one may say, hey, I would like to use GPU growth for predicting latency, and that's reasonable by just looking at the data. But let's look at the causal relationship between these. Actually, GPU growth is not the reason for changing latency. Is not the cause of this change in latency. Is actually just correlated because both latency and GPU growth have a common cause, which is swap memory. So this is known as a as a typical structure in BaseNet, right? When we have this AI course, right? This common cause is the situation that you have multiple variables, let's say X and Y, and both of them are have a common cause Z. In this case, if you look at data, X and Y might be totally correlated, but it's not the case that X causes Y or Y causes X. None of these is correct. Actually, they have a common cause Z, which basically made this correlation. And if we reason about this, if somebody uses GPU growth, it will result in a bad performance prediction if somebody else uses, comparing with the case that somebody uses swap memory. And this is why causal structure matters and why it is important to take into account for finding these causes in reasoning about performance. Rahul, do you have anything to discuss here?
Yeah, I mean, that was pretty much it. Like if we took each one and then started measuring the latency because we saw a strong correlation, we would find, like if you were to pin the GPU growth to two different values and just change swap memory, the figure on the bottom right shows that latency doesn't change much. So now the developer is confused because they saw strong correlation and they didn't know the causal model. It looks exactly the same. But if you reverse experiment and change swap memory from 1 GB to 4 GB, now the latency would be, the curve would be more pronounced.
Right, right.
So these kinds of correlations can be misleading, and just the, like you previously mentioned, the sheer number of combinations would make it impossible for one to try all pairs and see what works and what doesn't.
Exactly, exactly. And as Rahul mentioned, like this is only about one configuration option. And if we go back to massive configuration space, then you could imagine what would happen, right? Where we have many different variables in place.
And also like the external factors that affect swap memory, like external memory that you added, cannot be factored in, because if you have more external memory, then the curve would look significantly different than if you had less external memory for swap.
Right, right, exactly, exactly. Fantastic, thanks, Rahul. And if you consider, like, you can consider even more interesting scenario when it comes to transfer learning, right? And this is also a work that we are exploring from the theoretical perspective with Muhammad Ali. So imagine that we have a scenario where you have, you are interested, so the task is to predict X2. Right, so X2 is the target variable. So X2 is the variable we want to predict, and we have two potential predictor, X1 and X3. Okay, and this green crosses represent the source data. Let's see what happened, right? So let's imagine, for now, ignore this structure, right? Let's imagine we only have these data. Again, by looking at the data, these green crosses, we see that both X1 and X3 are correlated with X2, right? But X3 is much nicer predictor because it has less variance for predicting X2. So one may say that, hey, I'm going to use X3 as the predictor, and maybe I also consider X1 and X3. So these are my choices for using as the features or predictor for predicting X2. These are choices. Nobody say that I only consider X1. Why? Because it is too noisy, right? It's too noisy. Even though it's correlated, it's too noisy. Nobody says that I'm considering X1. But let's now move to the target environment. In the target environment, let's look at the data. X3, so these blue dots are the target environment. X3 has changed dramatically in terms of distribution. Now, X3, by increasing X3, X2 not only increase, but also decrease. So the distribution, we have a distribution shift. This is known in machine learning as distribution shift. In this scenario where we move to the target environment, we saw this distribution shift. Imagine what would happen to these models. Both of these models would get the prediction incorrectly, absolutely biased, right? The only predictor that could predict X2 accurately is actually X1, right? You see that the X1 was not affected by this distribution shift, right? By just looking at the data, we have no reason to use X1 as the predictor. But if we have basically the mean to exploit the causal structure, in the causal structure, you see that X1 is actually the only cause of X2, right? And X3 is just correlated with X2 because X2 is actually the cause of X3, not the other way around. And in this case, we know that this context variable would change the distribution across environment. So if we are able to intervene on X1, this would, by knowing the intuition behind BaseNet, we know that if we fix X1, the change in C1 would not affect X2, right? But we know that with this structure, this is a V structure, right? If we fix X3 in the common structure, if we fix X3, this opens up the information from the context variable all the way to our target variable, and that's bad because we open up a path between context variable that would determine the distribution shift across environment. So, but was it really possible to do this reasoning without having the structure? It's absolutely impossible. So in this case, it is absolutely impossible to do such separation, reason about performance when we move to the target. And this is the work that we are doing with Muhammad Ali. The existing approaches is not scalable to the size that we deal with performance for highly configurable system because they need to do automated theorem proving, which would not scale beyond 10 variables. Muhammad Ali came up with interesting idea by just looking at the Markov blankets, which is just the boundary between the target variable and the rest of the variables, and this would make it scalable to a large systems. This is what we wanted to do, right? So based on these intuitions, Rahul and Shahryar developed Cooper, basically that does two things. First, it localizes the performance faults. It gives you a reason, the root causes of these performance faults based on this causal structure that it discovered from the observational data, and also it finds automated repair for these performance faults. It is an iterative approach. We start by some observational data. We extract some causal structure based on some predefined causal structure discovery approaches, and then we do this iteratively until we find a repair for these faults. And the key insight in this approach is really using counterfactual queries. The key benefit of counterfactual queries, you can think about counterfactual query as a change in the system, specifically configuration, without really measuring anything new, by just relying on the causal structure. So we can estimate the intervention in terms of configuration change, and we can use this estimation to prioritize the potential fixes for these performance faults. And again, like this is about causal structure discovery, the important part, and we use some existing approaches. Muhammad Ali also done some interesting work with respect to causal structure discovery. If you are interested to know more, please look at some of these work, but I'm not going to talk about it. And again, this is iterative approach that that it measures some treatment effect based on these counterfactual queries and prioritizes, and it stops until we exhausted all budgets. So there is a question apparently, right? Could you please explain a bit more how the causal structure discovery works? Right, Miguel, unfortunately, we don't have much time, but basically there are causal structure discovery is its own area. For example, Muhammad Ali's thesis was about causal structure discovery. And it has different constraint-based approaches and some other approaches. But the key intuition is that imagine that you have some data, you run some independence test. So when you have some data about some variables, you want to look at whether these two variables are dependent or not. Then you want to run independent tests, which is a standard statistical test in a statistic, and determine whether there is a connection this way or that way or two-way, right? And do this with some constraint. And we know that the key challenge is the scalability. When we have many variables, this doesn't scale to like doing this like exhaustively for all pairs. If we have, again, we have the massive number of statistical tests we need to run. Mainly some people consider constraints between variables to scale this up. Muhammad Ali looked into Markov blanket stuff to scale this up, and others also came with some parameterization, active learning approaches for discovering this causal structure and so on. But this is beyond the topic that we want to discuss. But thanks for asking. This is a very relevant question. Yeah, obviously, we got some results. We compared with some statistical debugging, and we did better with respect to accuracy, precision, and recall for different type of system, machine learning systems, some data store and video encoder in different environments, right? I'm not going to talk about detail, but basically, we find that Cooper was able to find these root causes more accurately compared with the statistical debugging, which is mainly based on correlational analysis. And Rahul and Shahryar compared the performance with respect to, this is the result that we just got, compared with the SMAC. So SMAC is a performance optimization approach. And the key insight that we find out is that we either find similar, so our approach, Cooper, is not a performance optimizer. We just want to find a repair. We do not have any claim about optimization. But comparing with SMAC, we were able to either find comparable configuration with respect to performance, and in larger workload, in more crazier workload, we were able to find much better configuration with respect to performance in all objectives, right? So this is about heat, energy, and latency. But more importantly, we were able to find this considerably faster. So this is the amount of time that it took for finding this repair. This is about the time for our approach. This is about the time for SMAC. So considerably takes much more time to find this repair for with SMAC than our approach. And in transfer learning scenarios, we also try to reuse some of those good configuration from SMAC in the source environment and reuse that for predicting the performance in the target environment. And in all cases, it did really poorly. So the performance gain was not good enough when we moved from one workload to another workload, right? And this is only workload change. With other environmental change, we have not the results yet. So basically, this means that the best configuration would not stay the same if we change the environments. And we have observed this in our previous empirical studies as well. So it was good to see the confirmation here. I have to mention there are some other lines of work. Especially, I would like to highlight Miguel's work on white box analysis. He's doing some very fantastic research in terms of white box analysis, which is somehow a different direction than what we have been doing in terms of black box approaches. So this is based on some code analysis and some granular white box analysis. This would open up new opportunities for research in this direction. Rahul also has done a very interesting work on transfer learning with detail that was published in IEEE Transaction recently. So again, I would like to emphasize that today I just was the presenter. All the work has been done by this fantastic team. So I played very, very small role. Probably I just presented for you, but all the work is that I presented mainly, especially about this causality work, was led by Rahul and Shahriar. For all of these causality work, so Muhammad Ali, I mentioned that he was a postdoc in my group. Now he's at Purdue. We are collaborating with Bashaki Ray, especially on this Cooper. We have been collaborating with Christian, also Miguel, Norbert from Leipzig, Sven, Lars, Marco Valtorta, Vivek, and Tim Menzies. So thank you all for participating. It was a pleasure actually talking about this stuff with you. It was my honor, and thanks for organizer of ASC to giving us this opportunity. So to summarize, I mentioned about some challenges by elaborating on a specific system. I talked about this transfer learning stuff we have been doing, and some didn't get the chance to talk about this empirical study and provided some future opportunity and current work that we are doing. So I would stay here for as long as you want. I'm happy to discuss and answer any question if you have. Thank you, Fatima. Thank you, Miguel. Don't be shy. If you have any question, I would be delighted to discuss. And I have to mention that this is the line of work we are doing. And as always, I'm looking for to explore any future collaboration and so on. So please keep in touch. I would be happy to discuss.
Puyan, I have a question. So,
Yes, go ahead.
thanks for your talk. So how do you see this transfer learning or the causality inference that you mentioned in other areas other than performance analysis? Also, how do you see it in connection with the actual code? Such as, for example, program analysis. So how do you see that it can be used, or it can be, I don't know, combined or something like that in addition to the actual code analysis?
Yeah, that's a fantastic question. Rahul, do you want to answer? Because we just discussed with Rahul about some of the opportunities in program analysis.
Sure. Yeah, I mean, I would say the essence of causal inference is having a good graphical representation of variables and how they interact with one another. And I think the line of research that we're trying to explore is with, with code or any performance issues that arises with code. We have access to control flow graphs and program dependency graphs and so on. So a promising direction that we are currently exploring is basically modeling code using those graphical representations, and then using a lot of the mechanisms that are well established in causal inference to find, like root causes of performance faults, or what lines of code or modules in the code can potentially lead to faults in the system. So it can easily be extended. I think the essence is having a good graphical structure And when it comes to code, we have decades of research on modeling code in that way. So yeah, does that answer your question?
Yeah, that's actually great. So this is beyond the scope of this discussion, I believe, and yeah, but I do have something else I wanted to discuss is about the specifically the emergent behavior analysis. Um, so, for example, in multi-agent system, in all autonomous systems, there is a phenomenon called emergent behaviors, and then I also found that this is also a problem in some of the like Dell products just recently. That the difference between what is designed and what is implemented. So I know it is pretty different area of work, and we are not talking much about the numbers between the design, specifically when we are talking about the design. But maybe like, do you see any chance that the transfer learning can be used to find out those mismatches between design and implementation?
Right. That's a very deep question. It's beyond probably my knowledge that I could provide reasonable answer, intelligent answer. Uh, but basically, I presume you're talking about mismatch between a specification and implementation, right? Um,
Yeah, that like I said, this is I don't think this is a discussion that fits in a few minutes.
Yeah, this required deep discussion. This is so dense and interesting at the same time that probably requires some deep discussion about what
Yeah,
do we mean by a specification, what do we mean by implementation, and so.
exactly.
Uh, yeah, but I have to mention some of the work that mainly has been done by Katya and also Alda, Sarah, and also Andre. We have been doing some visualization work that exploring the different refactoring and how that could impact performance there. This refactoring is in terms of like changes we could do into the system, both at the architectural level and at the implementation level. Um, there are some connection there I could see, but I cannot really elaborate enough at the moment about this question.
Interesting. Yeah, thank you.
Sure. Thank you, Jay. I will stay here as long as you have question. Please bring it up.
So let me ask one. Since you want questions, thanks for a great tutorial, Brian. That was excellent. So what was the now that there is a bit of time, could you elaborate a bit on the techniques used for finding the causal inference? For what techniques you use in order to establish those graphs?
Yeah, maybe either Shahriar or Rahul wants to elaborate on this. We used FCI there, but maybe Rahul could elaborate more.
Sure. Yeah. So like Boyan mentioned, there is a long line of research on finding causal graphs, and we particularly used an algorithm called FCI, which stands for fast causal inference. The idea on a very high level, and we can share some resources on this as well. The idea on a very high level is to basically use independence tests between pairs of variables and eliminate connections between edges that are independent. And then there are certain rules called edge orientation rules, which assigns directionality to the edges, like the ones shown here. And the amount of data that's available determines what the direction of the edges are. And after that, it's a rough estimate of the causal graph. And if you have a subject matter expert at hand, they can help remove edges, directed edges or undirected edges, which shouldn't be there. Or we could use other optimization-based techniques to get a DAG. The goal with causal graph is it should be a directed acyclic graph. So there shouldn't be any cycles and all edges should be directed. And basically any algorithm that can get a graph structure from observation data can be used to see a causal graph. Does that answer your question?
Yeah, that's perfect. Thank you.
Thanks.
You're welcome.
It's good to see you here.
Good to see you too.
Any other question? So if there is not any further question, let's end it here. Thank you very much. It was a real pleasure to talk to you guys, and please keep in touch. So anytime I would be delighted and happy to discuss opportunities, and thank you. Have a great weekend, I would say.
Thank you.